So let's look at an example of a friction problem where we have a box that's being pushed along the floor with a downward force being applied by, let's say, a human pushing down with their hand. And so here's the mass. It's on a level floor. There is friction. And here's a force diagram. So what we would do first off is to assume a coordinate system, which I have sketched over here. X positive to the right, y positive up. And I would break this downward slanting applied force into an x component, which is F cosine theta. You see I have the angle theta labeled as being the angle between the horizontal direction and in this F slanted down. So F cosine theta is the x component of the force, and F sine theta is the y component of the force. So the free body diagram then, with the F broken up in this way, is going to have mg and F sine theta pointing downwards and n pointing upward, F cosine theta pointing off to the right, and then some frictional force impeding the motion. And so please look at this picture and realize that that n is bigger than mg. And you see it has to be because n has to counterbalance not only mg, but it has to also counterbalance this F sine theta. Now, I can write a Newton number 2 in the y direction and the x direction, and so in the y direction, in which direction I do not have any acceleration, and in which direction, therefore, the net force has to be 0, is n minus mg minus F sine theta. Again, note how I am bookkeeping the directions for mg and F sine theta with negative signs, consistent with my assumed coordinate system. And this equation is equivalent to n equals mg plus F sine theta. So I have an expression for the normal force. In the x direction now, the x direction gives me an equation that the net force in the x direction is F cosine theta minus whatever frictional force I have. And that's, by Newton's second law, going to be equal to m times a sub x. So let's consider two cases. Let's consider case 1, where, as you will see, m does not move, and case 2, which I've chosen the numbers that m will actually accelerate. And furthermore, let's plan on using an m of 2 kilograms, which would give me, with easy numbers, a weight mg of 20 newtons. And let's assume mu sub s is equal to 0.4 and mu sub k is equal to 0.2. Again, mu sub s is always bigger than mu sub k. And so for this first example, let's say that the applied force, this downward slanting force, is 8 newtons, and it's applied at 30 degrees with respect to the horizontal. Well, in that case, F sine theta would be 8 newtons times the sine of 30. Sine of 30 is 1/2, and so the y component would be pointing down with a magnitude of 4 newtons, and F cosine theta would be 8 newtons times cosine of 30. So grab your calculator and you will see that that is 6.9 newtons. I am retaining 1 decimal point in these calculations. And so from our Newton number 2 equation, in the y direction, we know that the normal force n is mg plus F sine theta. And so for this example, that would be the weight of the mass, which is 20 newtons, plus F sine theta, which is 4 newtons. And so the normal force is 24 newtons. And we can also calculate the maximum force that static friction will give to impede this F cosine theta, and that's going to be the coefficient of static friction times the normal force, which is 0.4 times 24, which is 9.6 newtons. And since F cosine theta is 6.9 newtons, and that's less than the maximum 9.6 newtons that can be provided by the coefficient of the static frictional force, that means a sub x is going to be 0 meters per second, and m does not move. We're not pushing hard enough at this angle. Okay, so in example 2, what we're going to do is we're going to keep the angle the same, and we're going to quadruple the force. And so instead of pushing at 8, I'm going to push at 32 newtons, but again downward in the same direction. And so in this case, F sine theta sine 30 will be 16 newtons, 4 times what it was before, and F cosine theta is going to be 27.7 newtons, 4 times what it was before. And the normal force is now the weight plus this extra downward component of F, which is 20 plus 16. In other words, the normal force is 36 newtons. So the normal force has gotten bigger. And so now we need to compute to see whether the object moves or not at all, has any acceleration. We first of all compute the maximum frictional force, and that's always given by the coefficient of static friction times the normal force. So in this case, the normal force is 36 newtons, and the static friction coefficient of friction that we're assuming is 0.4, and so that's going to be 14.4 newtons. But since our applied force in component of that in the x direction is 27.7 newtons, and that's bigger than 24.4 newtons, that means it is going to move. The acceleration is going to be bigger than 0. And furthermore, we need to use mu sub k. Since it will be moving, we have to use the kinetic coefficient of friction. And our a sub x now, so I'm going to take my Newton number 2 equation here and solve for a sub x. That's very simple to do. Just divide both sides by m. Is f cosine theta minus s sub f over m. And this now is the 27.7 newtons, which is the x component of the force. And for s sub f, I now transition to the coefficient of kinetic friction, 0.2 times the normal force, which is, as we've previously computed, 36 newtons divided by 2 kilograms. So that leaves us with a numerator of 20.5 newtons divided by 2, which is 10.3 meters per second.